In this lecture, we're going to continue talking about stoichiometry. And now we're going to move past mole to mole conversions and talk about mass to mass conversions. And this is where we're going to get our true three-step dimensional analysis stoichiometry style problem, where we can be predictive about the amount of products that will form or determine how many of our reactants we need to combine in a reaction mixture to produce what we need. So we're going to walk through an example problem step by step to show the problem solving strategy you're going to use for these. In general, you're going to follow 4 steps. You're going to make sure your chemical equation is balanced. Then you're going to convert the mass of what you know about into moles. You'll then do a mole to mole conversion into the compound that you're interested in learning the mass of, and then convert the moles of that compound into the mass. And so those second, third, and fourth steps can really be combined into a one line of dimensional analysis that has three conversion factors in it. Sorry, 3 conversion factors. So the practice problem we're going to look at is propane combusting with oxygen to form carbon dioxide and water. We're going to start with the knowledge that we have 25.3 grams of carbon dioxide, and we want to know how many grams of oxygen are consumed. So typically when we first introduce stoichiometry problems, we always take a reactant and predict an amount of product. And since you've already had an introductory chemistry class that's leading up to this one, I know you've probably seen this already. So we're going to start backwards. We're going to look at a product amount and predict how much of a reactant is required to produce that amount of the product. And that's the beauty of stoichiometry. We can start from any point in our chemical equation and convert into the amount we need or will produce of another compound, either as a reactant or as a product. So it's really versatile. It does mean recognizing where your starting point is. And so here, if we're starting with 25.3 grams of carbon dioxide, we're starting with a product. And then we're going to be converting into grams of oxygen. So we want to know about this reactant. All right, so let's walk through it. So step 1, we are going to balance this chemical equation. And we'll just walk through this. It looks like I already did it. There we go. So we'll confirm that this is a balanced equation. So we have a 3 right here in our front of our product, carbon dioxide, because we have 3 carbons in our reactant. We have 5 times 2, we have 10 oxygen atoms. And that's going to be balanced by 3 times 2 oxygen from our carbon dioxide, which is 6, plus the 4 times 1, which equals 4 oxygen atoms from our water, which will be 10. So we have the same number of oxygen atoms on both sides too. For our hydrogen, we have 8 in our reactants, and we have 4 times 2 in our product, so we have 8 in our product as well. So we have a balanced equation. So step 2 is going to be convert mass to moles for our given amount that we have, which we know is going to be 25.3 grams of carbon dioxide. So let's do that. This is going to require a conversion factor. If we have 25.3 grams of carbon dioxide and we want to convert this into moles of carbon dioxide, we need a conversion factor that puts moles on the top of our fraction and grams on the bottom. And so looking at that, I recognize it as molar mass, or the inverse of molar mass, which we can calculate from the periodic table. So this isn't a conversion factor that's given to us. In fact, none of the conversion factors we use in stoichiometry are going to be written out in the problem. They're all going to be extracted from the chemical equation and the chemical formulas that are given to us. So we need this for carbon dioxide, and we can go to the periodic table and we can do 12.011 plus 2 times 15.999. That oxygen mass is 15.999. Carbon is 12.011. And we'll get that there'll be in each 1 mole of carbon dioxide, there'll be 44.04 grams. Sometimes it's 01. It depends on the periodic table you're using. They all have a different number of digits. Okay, now I have something simple I can plug into my calculator. 25.3 divided by 44.04. And when I do that, I get 0.574869. I'm going to track my sig figs. I've got 3 sig figs that I measured out initially. So I'm going to underline my third significant figure in this answer and carry all of my digits forward into the next calculation, but track my sig figs. All right, so now step 3 is to convert moles to moles. So I'm going to take my carbon dioxide moles to oxygen because we're asked what mass of oxygen is produced. So I'll set up my conversion again using dimensional analysis. I have 0.574869 moles of carbon dioxide. I'm going to multiply that by a conversion factor that'll produce an answer in moles of oxygen. So I need a conversion factor that puts moles of oxygen on top and moles of carbon dioxide on the bottom. So I'm going to go to the coefficients of my chemical equation to get that conversion factor. So looking at that, I have these coefficients in front of each of my particular molecules. So I know that from the coefficients, 3 moles of carbon dioxide will equal 5 moles of oxygen. And that's just coming from the coefficients in front of them. So I'll plug in a 5 in front of my moles of oxygen and a 3 in front of my moles of carbon dioxide. And I'll plug this into my calculator. That 0.574 times 5 and divided by 3. And when I do that, I get an answer that is 0.9581156. I'm going to track my sig figs still. I'm still at 3 significant figures. And now I'm ready to do the next step, the fourth step of this problem. So now that I have moles of oxygen, I at least have an amount of the molecule that I'm interested in, right? And we wanted to know the amount of oxygen. But we need this in mass. So now we're going to convert moles to mass. And so we are starting with our 0.9581156. And that is our moles of oxygen. I'm going to multiply this by a conversion factor to get an answer that's in grams of oxygen. So on the top of that conversion factor, I need that unit of grams, and I need moles of oxygen on the bottom, so that way those units cancel out. And that's molar mass again. So this time it's going to be the molar mass of oxygen, though, because of that moles of oxygen and moles of grams that we're going for in our answer, and the moles of oxygen that we need to cancel out. So I can calculate that by taking 2 and multiplying it by 15.999, and I'll get 31.998. And that's 31.998 grams in each mole of oxygen, molecular oxygen. So I can now just multiply this. And when I plug it into my calculator, I get a value that's 30.65778 grams. And again, I'm looking at 3 significant figures. And so this is going to be an answer of 30.7 grams. And that's the amount of oxygen that I'll produce. So that's 3 different steps that I could actually string all together into one problem to plug into my calculator as well. And the way that would look, if I can create a little space here. There we go. I'll do this out here at the bottom. It's if my starting point was 25.3 grams of carbon dioxide. I would first convert that into moles. Let me get a little more space there. With the molar mass. Then I would do the mole to mole conversion for the second step. And then I would convert into mass for the third. And if I look at how the units cancel out here, I'll see that my grams of carbon cancel, my moles of carbon dioxide cancel, my moles of oxygen cancel, and I'm left with grams of oxygen. And so as long as I'm providing context to those units with the chemical formula, I'm able to still use dimensional analysis to figure out how to make this problem work. So if I've really beefed up those dimensional analysis conversion skills, I can just lean on those through stoichiometry problems when I'm feeling confused or lost.